Okay, so let's wrap up this report. We can jump some of these things because we've already looked at these in detail elsewhere. Enhanced rock weathering, of course, there is mining of rocks, grinding of the rocks with alkaline materials like olivines, here mineral olivine, being transported somewhere and distributed over land areas, so carbonate and other reaction products are produced. So high atmospheric CO2 air, high CO2 atmospheric air uh, reacts and produces reduced CO2 air, obviously, and you sequester the carbon into various forms. Could be agricultural land, forest, or just land that is taking up uh, carbon into the soil. So it's a once through process because you cannot recollect and recycle those materials. Ground rock containing alkaline minerals are needed as inputs, and carbonate rocks and other carbonate ions and products like silicon dioxide are produced as outputs. Total energy requirements, including for mining and processing, are likely less than for cyclic systems, which is an advantage, but this requires large amount of mining and processing as a potential drawback. What are the uncertainties and research opportunities? Well, rate and effectiveness are unclear. Measurement reporting and verification is difficult because you put this out on land, you know you are increasing CO2 in the soil, which can be measured, but how much net CO2 was actually drawn down is not very easy to verify at all. So environmental consequences of distributed reaction products may also be unknown, and some that may include heavy metals, which you definitely don't want in the soil, or foods and water and so on and so forth. Okay, so this is the peridotite in the Trinity Alps of Northern California, showing orangish weathered surface and freshly exposed dark surfaces, which is the natural process you are trying to use for enhanced rock weathering. And view from space of a 45 square kilometer Ice Springs basalt lava flow in Utah, which is part of the Cinders volcanic complex, has a total volume of 5.4 times 10 to the 8 million cube, and big. Okay, so assuming the basalt has a density of 2.9 grams per centimeter cube, the flow has a mass of about 1.5 gigaton. At a conversion rate of 0.3 tons of CO2 per ton of basalt, this source could remove about half a gigaton of CO2, depending on the time scales on which you are doing these things. So again, natural processes that can be exploited. Ocean alkalinity, again, we have looked at before. You again taking mined and ground up alkaline material in a ship and putting it into the ocean, and you are increasing the pH, and that forces CO2 into the water and produces carbonate ions, which can offset the acidification. When you have increased CO2 in the atmosphere and ocean acidification happens, there are a number of reactions, but basically you are eating up or absorbing CO3 minus carbonate ions, which are very essential for things that grow in the ocean that have calcium carbonate shells, like corals and various other shell forming animals. So since ocean is buffered, it can keep taking more CO2 if you keep increasing pH. Ocean has regulated its pH, alkalinity, and so on for millions, tens of millions of years. So now we are moving it maybe rapidly and monotonically towards lower pH, so you want to increase pH to enhance these reactions that naturally occur through, water is highly a good solvent for CO2, but alkaline water takes up much more CO2 through these buffering reactions, which means it doesn't easily get saturated. It moves CO2 dissolved into bicarbonate and carbonate ions and so on. So this is the once through process. Obviously, ground rock containing alkaline minerals are needed. Dissolved alkaline material and increased carbonate in the ocean surface waters is produced. The advantages are that total energy requirements likely less than for cyclic systems. Reduction in ocean acidity may positively impact some ecosystems. Potential drawbacks, of course, requires a large amount of mining and processing and shipping and distributing, and there is life cycle analysis needed. Uncertainties and research opportunities, then rated effectiveness still unclear, like rock weathering, enhanced weathering. Measurement and verification, of course, very difficult even compared to land. Environmental consequences of adding large quantities of alkaline materials and trace elements to oceans are not understood well at all. Okay, so summary of carbon storage and sequestration, we don't need to read too much of it. There are many approaches. CO2 can be let's just read it. A straightforward approach to carbon storage and sequestration involves compressing the CO2 to a supercritical fluid and injecting it into an underground reservoir where it remains trapped for geologic time periods, hopefully. So under some circumstances, the CO2 can gradually mineralize underground. Studies suggest that underground storage sites are available that could accommodate many thousands of gigatons of supercritical CO2. Supercritical means energy requirements. There do not seem to be any fundamental obstacles to implementing this type of CO2 sequestration at large scales, but concerns such as leaks and earthquakes need to be addressed. Other approaches for dealing with captured CO2 include mineralization and use in long-lived construction materials such as concrete. These methods are less developed though. So summary of measurement, reporting and verification, other systems. I won't go into it, but building coherent and effective portfolio of CDR systems requires better understanding of the risks and potential environmental impacts of different approaches. Also requires a coordinated approach to implementing CDR systems in appropriate geographical locations in combination with energy sources and storage sites, and with consideration of land use and energy issues. But basically progress cannot be monitored, especially for corporations and others who may start using CDR as an offset to say that to make sure that they are actually sequestering carbon and not just claiming things, especially for ocean alkalinity experiments and ocean alkalinity enhancement and enhanced rock weathering. If it's hard to monitor, measure additionality, then it can easily become a loophole for offsetting people. And costs matter, of course. So if the price can be reduced to 100 to 200 per ton of CO2 for engineered CDR systems, that would correspond, for example, to a cost of $1 to $2 to capture carbon released when an automobile burns a gallon of gasoline. So you can see how many fossil fuel cars may be still in existence and how we may end up capturing them, at what cost they become economically feasible, and so on. So let's read off the overview, conclusions and recommendations. Modern society depends crucially on access to extensive and reliable energy, and fossil fuels have provided a compact and economical source of such energy over the last century. There are various strategies depending on wealth, resources, politics and societal values that countries independently or through international agreements may use to balance energy needs with concerns about the ongoing rapid increase in atmospheric carbon dioxide levels. So China, India, other countries that are trying to develop will use whatever energy they can find, but they are also playing the international participation game with their nationally determined contributions to be good citizens in climate action. So emissions reductions are of course needed. CDR methods as described in this report to extract excess CO2 from the atmosphere and or balance ongoing emissions from difficult to transition technologies are critical. So these are actions. Solar radiation management, we have discussed it elsewhere, remains tricky and controversial because you are going to spray things in the upper atmosphere hoping to deflect or reflect sunlight to reduce the amount of energy coming in. But if CO2 continues to rise, then you're going to have acidification and other negative impacts. And if SRM, solar radiation management, is stopped, then what happens? So these are tricky questions. Adaptation, of course, where feasible, offset the undesirable consequences of warming and adapt systems to accommodate changes in climate. and that's very obvious. We discussed it extensively elsewhere. What are the science-based conclusions and guidance for policymakers? Here are the summaries. We'll look at a table in a minute. Large-scale CDR requires substantial energy inputs and massive material infrastructure that we already discussed. So you have to keep that in mind when you want to keep scaling up CDR if and when they become scalable and technologically ready for doing that. So maybe there is no Moore's law for CDR. You know, the Moore's law comes from computers and how the growth in computing speed, power, becomes limited and so on. I won't go into the details, but optimistic view there in terms of not having a Moore's law for CDR. CDR at the gigaton per year scale may be desirable in the coming decades to meet specific climate goals, so research and development on a variety of CDR approaches is recommended despite their extensive energy and material needs. So experimentation to show feasibility and then advances in engineering and energy production to reduce the energy needs and negative impacts of materials mining and so on have to be carried out at research stage so that we know we can do it and how we can do it. So there are potential numbers mentioned for electricity needed and so on, and obviously they are estimates. For practical purposes, a portfolio of different approaches would likely be needed to achieve capture and sequestration at very large scales. These technologies are rapidly evolving and new ideas of CDR continue to emerge, so care should be taken not to prematurely commit to a specific approach that may soon be superseded. Depends on the investment. If you're going to invest $1 billion in something and that becomes much less efficient and more expensive than a newer method, then how quickly can you disinvest from those older methods or inefficient methods? Efforts to reduce carbon emissions should not be compromised by possibility of future large-scale atmospheric carbon dioxide removal. So CDR is not a substitution for burning continued fossil fuel. In other words, you cannot continue to burn fossil fuels and hope CDR will deal with it. You have to reduce carbon emissions in energy and all the other transportation, buildings, agriculture, and so on and so forth. Ecosystem-based CDR approaches, natural climate solutions as we call them, should be pursued where feasible and effective in the near term so that they can help bridge till we get CDR in complete operational scalable stage. So there are many challenges, of course, that can help restore lost soil and biomass carbon at gigaton scale with site-specific changes in land use practices over large areas. Of course, that's difficult to ensure that carbon is retained in the soils over long times, because with warming, respiration goes up, human perturbation of ecosystems continues, and urbanization continues, etc. Right? Any substantial development of CDR systems, particularly cyclic systems such as DAC, should be done in combination with dedicated low-carbon and carbon-free energy sources. And there is a general argument that the entire system is now a carbon trap, so we must decarbonize the system and not just keep the paradigm of trying to reduce emissions, because all these negotiations to reduce emissions haven't worked and our emissions keep going up. So the source of energy becomes a critical consideration, but decarbonizing the system means energy is going to be clean. Economic and policy framework should be put into place to balance emissions with removal costs. So how the per ton CO2 drawdown cost is measured, what is the carbon cost in terms of social impacts, etc., need to be worked out. So we definitely need to bring down the costs as little as possible in terms of dollars per ton of CO2 in the very near future. So there is a scaling up needed, and there is a cost down needed. So both have to happen, and emissions reductions have to happen. Investments in locking in fossil fuels, like we talk about cars, if we keep producing internal combustion engines and invest more into building new infrastructure for producing them, then removing them from the system to decarbonize is going to be very challenging. So we need to move quickly to electric vehicles and so on. It's important to develop reliable systems of measurement, reporting and verification, so that all the loopholes for greenwashing and so on have to be removed. Transparency has to be imposed. Obviously, these will be within boundary efforts as well as international efforts to do this. Summary of issues and recommendations then for different types of CDR. We are looking at types of CDR, primary physical constraints, other potential issues and recommendations. So let's just read these. Engineered cyclic, such as chemical DAC, energy requirements, cost and scale are issues. We need to pursue research, development and pilot projects to develop cost-effective and scalable approaches. Once through approaches like enhanced rock weathering and ocean alkalinity, enhancements need materials and they are uncertain in terms of their effectiveness and environmental impacts, unintended consequences. Recommendation is to pursue further research on impact and effectiveness before considering large-scale deployment. Lots of experiments already happening. Ecosystem-based approaches such as reforestation, nature-based solutions, reducing agricultural emissions, enhancing land sinks and so on. Energy, land, water are a critical constraint and they have limited capacity. Verifying effectiveness and longevity can be a potential issue. Pursue further research on monitoring, reporting and verification as a recommendation. Deploy where effective and economical, particularly where there are co-benefits for biodiversity, conservation, ecosystem services, water quality, groundwater recharge, and so on and so forth. So science-based guidance for funding pilot programs, then I think I'm basically at the end. This section is aimed at funding agencies and investors who are considering proposals for pilot programs and or demonstration plans implementing potentially scalable technologies for carbon capture. There are lots and lots of private players in trying to do CDR because they see this as a way to make a lot of money, not only directly capturing and making money from governments and so on, but also offsetting for those irreducible emissions and selling the technology to poorer countries, etc. We provide a set of key questions that should be considered in evaluating the possible challenges facing any CDR program or implementation, including both cyclic and once-through approaches. How much energy does the underlying set of physical processes require, whatever is the approach? What is the estimated actual energy cost for the full system, especially when you scale it up to multiple gigatons? Where will the energy come from? What will be the source? How clean is it? What carbon output will be associated with producing this energy? If low temperature thermal energy is used, are expectations for energy needs comparable with the second law bounds and underlying energy requirements? What are the materials needed? Are they available? How hard is it to transport them, store them, use them, reuse them, whatever? Is there a realistic framework for the integration of all parts of the system, from the material needs in production to deployment to the sequestration of captured carbon, so full life cycle, technology readiness level? What are the plans for scaling up from a pilot program to tens or hundreds of millions of tons of CO2 per year to eventually reach gigatons and tens of, money gigatons? What MRV approaches are available and how reliable are they in terms of ensuring actual additional carbon sequestration and their long-term storage and leakage, damage, etc.? What are the risks and potential impacts on land and oceans, and how well are they understood? For cyclic systems, the questions regarding energy inputs are particularly relevant, although material needs, impact, and scaling issues should be considered. For once-through systems, questions regarding material needs, verification, effectiveness, longevity, and environmental impact of the output streams are particularly important. Energy needs and scaling issues should also be considered. Okay, so a nice report, and lots of very good points, some additional to what we have already discussed, some re-emphasize some of the points. So I hope this set of podcasts is really useful. And always remember, I'm very brief and take material based on my own view of what is the most salient point I want to convey. The report is available, so you obviously want to go and read, and obviously there are lots of very, very good references that are also useful. Okay, so I'm going to leave it here. See you in the next topic.